Okay, can everybody see my screen? Thumbs up lang if you can. Okay. So let's finish the discussion that we had on biasing. When we last met, I emphasized the importance of biasing your MOS transistor amplifier properly. What we did in the last meeting is we showed that this is the voltage transfer characteristic of your MOS amplifier. Okay. If we apply this input, we want the output to be a good reproduction of the input. Now, to do that, we show that we have to bias the input properly. How do you bias the input? This is the signal that we want to amplify. To bias the input, you have to add a bias voltage. So our bias voltage is actually this. This is the bias voltage. If we don't add this bias voltage, our signal will be down here. And we will just be here in cutoff all the time. If we make the bias voltage too large, our signal will be out here and we will be in the linear region all the time. So remember that this is cut off. Remember this is cut off. Okay. And then this is your linear. Sorry, not linear, no? Saturation, sorry. This is your saturation. And then this is your linear. By the way, sometimes instead of saturation, we say active. So it's very important that we properly bias our transistor. Now, what is the easiest way of doing that? I mentioned the easiest way of doing that is just by connecting a voltage to your gate. And then how do you apply your input? You would apply your input by just capacitively coupling it. So we can do that. So this establishes the bias, and then this capacitively couples your input to your gate. So this is V small n. And the voltage at this point will now be a combination of your bias voltage and your input voltage. So this is going to be V capital N. But we also mentioned that this is impractical. For example, if that's an integrated circuit, we have two inputs, then you're going to have two extra supply inputs in addition to your main power supply. No, we don't like that. We want to be able to derive our bias from the main power supply through resistive circuits. So the bias voltages derived from the main power supply through resistive circuits. The same way we did for your transistor, no, your BJT, bipolar junction transistor. The easiest way of doing that is just by voltage divider. Okay. We want to know, or we have an idea of what the gate voltage should be. No? Let's say we already computed what V sub G should be. Alam na natin kung ano yung value ng V bias na gusto natin. So ito yung value ng V sub G. How do we establish the value of V sub G? We just establish the value of V sub G using a voltage divider. Just a while. Okay. So V sub G is equal to VDD times RG2 over RG1 plus RG2. No? Now we can use the voltage divider formula because I of G is equal to 0. If you remember your BJT, in the BJT, Okay. We also had the voltage divider biasing in your BJT, no? So how did that look? That also looked something like this, where you VCC, no? But why could we not use the voltage divider formula here? We couldn't use the voltage divider formula here because your I sub B is not equal to 0. No? So cannot use voltage divider. But in this case, since I sub G is equal to 0, you can use the voltage divider formula. Okay. So if we know the value of V sub G, it's just a matter of choosing RG1 and RG2. So if we know what V sub G we want, just need to choose appropriate values for RG1 and RG2. Now your considerations, there are three main considerations. Number one is your power consumption. Okay, what do we want the values of RG1 and RG2 to be? Do we want it to be large or do we want them to be small? From the point of view of power consumption. Can anyone shout out an answer? Anong gusto natin, no? Gusto ba nating malaki itong mga values na to or maliit? Anyone? Come on. Somebody must have an answer. No one? I'm very disappointed. No? Okay, if you want your power consumption to be small, you would want large resistances. Because the larger your resistance, the smaller the current, and therefore the smaller the power consumption, your I squared R. However, large resistors result in large areas. So if this was an integrated circuit, then okay, a large resistor would require a very large area. So there's a trade-off between space consumption and the size of the resistor that you are using. Okay, and then the third consideration is the resistance seen by the input signal. Eventually, we're going to have to connect our input, no, V sub I, that will be capacitively coupled to your gate. And this will see a certain resistance value, we call it R sub I. And that resistance value would depend on RG1 and RG2. No? Now, don't worry about that for now because we're going to take that up when we take up small signal analysis. But then that would affect our choice for RG1 and RG2. Because R sub I, sometimes you want this to be very large so that there is no load for your input signal. But other times you want to match this with the resistance of my source for maximum power transfer. Okay. Are you guys okay? I just want to make sure you're still there. No? Can you give me a thumbs up if you're okay? Okay. Okay, now there's a problem with this biasing scheme. No? We call this fixed biasing. This is fixed bias for your MOS transistor. Remember, we also had fixed bias for your BJT. The fixed bias for BJT is we fix the value of your base current. Here, the fixed bias for your MOS transistor is we fix the value of your gate voltage. If we fix the value of your gate voltage, okay, and I of D changes, no? Why will I of D change? I of D might change because of temperature, or I of D might change because of manufacturing process variations. So it's possible for I of D to change. One is by temperature, because, for example, your mobility is a function of temperature, your threshold voltage decreases with temperature, and yeah, those two. No. The other possibility is your process variations. Okay. From device to device, for example, your oxide capacitance can change due to process variations. So all of those can cause I of D to change. Okay. So even if this is fixed, no, if this is fixed, we want to have a mechanism whereby, in case there's a change in I of D, there will be a feedback so that it will try to bring I of D back to the intended value. Otherwise, the change in your Q point could result in distortion. So this is very similar to what we said for the BJT. We don't want IB to be fixed, because IB being fixed will mean IC is fixed. Okay, and sometimes we want IC to self-adjust. So how do we do that? No? Similar to the BJT, the way you do that, one way of doing that rather is by adding a source resistance RS. This is a resistor between the source and the ground. So this allows the quiescent value of your drain current to correct itself in case there are changes in temperature or process parameters, which would cause your drain current to either increase or to decrease. Now, let's take an example. No? What if I of D increases? If I of D increases, for example, due to temperature change, what will happen? If I of D increases, the voltage across this resistor will also increase. No? VRS will increase. Now, this is the voltage at your gate is fixed. No? Okay. So if the voltage at your gate is fixed, what is VGS? VGS is VG minus VRS. So if this increases and this is fixed, this will decrease. Okay. So decrease in VGS will mean a decrease in I of D. So this is how, in case this increases due to temperature, this will provide a voltage feedback that will cause VGS to decrease. That in turn will make I of D tend to go back to its previous value. So that is how we obtain stability in our Q point. Are there any questions with regard to that? I hope you understood that. Okay. Okay, I have this exercise. I did this with the earlier class. It took a while. Let's just try it together. No, I don't think we have time to try this. It took quite a while for the original class. No, so okay, the NMOS transistor has a VTH equal to 1 volt, Kn equal to 2 milliamperes per volt squared. Determine the required value of R1 so that the operating point of the circuit is at ID equal to 2 MA. And validate the operating mode of the transistor under these conditions. So we want ID to be 2 MA. This is our Q point, our desired Q point, 2 MA. So for this to be my Q point, what value of R1 should I select? Okay, so first let's assume saturation. Later on, we'll validate that our assumption is correct. I know that ID is equal to 1/2 Kn VGS minus VTH squared in saturation. So what is this? Is 1/2. Case of N is 2M. to MA. Okay. VGS, VTH is 1 volt squared. And I know that this is 2 MA. So this cancels out, this 2 and this 2. The M here cancels with the M there. So I get 2 is equal to VGS minus 1 squared. I can compute for VGS. VGS is the square root of 2 plus 1. That's equal to VGS, which is about 1. This is about 2.414 volts. Thereabout, no? 2.414 volts. So that's the value of VGS here. Can someone tell me what the voltage across RS is going to be? Anyone? Can someone tell me what the voltage across RS is going to be? Please, someone try. Ano yung voltage across RS? No idea? Nobody has any idea? Let me make the question easier. No? What is my current IS? What is my current IS? What is my source current? Anyone? Hmm. No one? Well, I guess I'll have to. Okay. Is of S is always equal to Is of D. No? Because Is of G is equal to 0. So this is very basic for your MOS transistor. Therefore, Is of S is also equal to 2MA. And therefore, VRS is just Is of S times Rs of S, which is 2 volts. Okay. So the voltage across Rs of S is equal to 2 volts. This is minus 5 volts. If I have minus 5 volts here, and I have 2 volts across Rs of S, then that brings my voltage here to minus 3 volts. Okay. Because if this is 2 volts, then I have minus 3 minus minus 5 is equal to 2. So this is minus 3 volts. And therefore, what is VG? VG is just V of S, V of S plus VGS. So this is minus 3 plus square root of 2 plus 1. So I'm going to get square root of 2 minus 2 volts. So that will be the value of V of G. So now it's easy to determine Is of 1. I just use, okay, KCL on the gate. Okay, so what is this? VG minus 5 over R1 plus VG minus minus 5 over R2 is equal to 0. I know VG, I know VG, I know R2. I can solve for R1. No? I can solve for R1. So I'll just leave this for you to do on your own. Now, the other part of the problem, validate the operating mode of the transistor. It's quite easy. All you have to do is compute for VDS. If you have 2 volts here, 2 volts here, and then the difference between the voltage here and the voltage here is 10 volts, then you're going to see that VDS is equal to 6 volts. So VDS is just going to be equal to 6 volts. Now, you know that it's in saturation if VDS is greater than VDS sat. What is VDS sat? VDS sat is VGS minus VTH. No? My VGS is Sabay yung VGS ko. This is my VGS. VTH is equal to 1. Obvious, no? 6 is going to be greater than 2.414 minus 1. So this is going to be correct, no? So that's how you validate if that is in saturation. Okay. Please, no? This is an appeal. Please study how to do these calculations. I'm getting a sense. I'm really getting a sense that right now, at least for the people attending this session, right now you don't have a feel for how to do this. No? And this is something that you should have learned in 1, 2, 3. So if you're having a hard time just doing these calculations, you're going to have a very difficult time going through the rest of the course. No? So my appeal to you is please try to practice solving problems ng mga ganito. No? Because this is very, very basic. If you're having a problem now, you're going to have much bigger problems later on. Okay. Okay, I'm going to discuss drain to gate bias. This is a very simple biasing scheme. It can be used as an alternative method of biasing your MOS transistor. Here we needed 2 resistors. No? In this case, we needed actually 3 resistors, RG1, RG2, and RS. RS to provide stability. This one already provides a certain amount of stability. This provides stability, provides some stability. Okay, but the only thing that you can play with is RD. However, R sub D is the only parameter we can adjust. The value of R sub G is immaterial to the bias point because the current flowing through R sub G is equal to 0. So regardless of the value of R sub G, the voltage drop across R sub G is going to be equal to 0. That will always put your gate at the same voltage as your drain. No? So if this is V sub G and this is V sub D, V sub G will always be equal to V sub D. No? Because the voltage drop across R sub G is equal to 0. Okay, this acts like a feedback element. No? Why? No? If I sub D increases, V sub D decreases. If this increases, the voltage drop across RD increases, and this voltage will decrease. If this voltage decreases, then V sub G also decreases. No? Then V sub G will also decrease because V sub G is equal to V sub D, and therefore I sub D will decrease. Because I sub D is a function of VGS, VGS is equal to V sub G. So that's what provides the feedback. So R sub D in this particular case actually provides the feedback, provides a feedback voltage. And that is what will tend to stabilize I sub D. Now, the reason why this might not be that popular biasing scheme is because R sub D is also important in establishing the gain of the amplifier. So if we have to adjust the value to properly bias the transistor, we may not get the gain that we want. Okay. So that is, there are trade-offs, no? So trade-offs needed because R sub D is needed to establish the amplifier gain also. So we don't have that much freedom, for example, to choose the value of R sub D. Okay, I have an exercise here again. Please try to do this on your own. Okay, this is a very important topic. This is current mirror biasing. Current mirror biasing is a technique that is very commonly employed when designing integrated circuits. So for those of you that are going to go into microelectronics, you're going to encounter current mirror biasing when you design integrated circuits. So what I show here is your basic NMOS current mirror circuit. I have two transistors, Q1 and Q2. The assumption is Q1 and Q2 these are fabricated using the same process. And therefore have identical process parameters. Identical process parameters. What are these process parameters? No? For example, threshold voltage. They would have identical threshold voltages. They would have identical oxide capacitance. No? They would have identical, in this particular case, mobility, and so forth. No? Now, if they are fabricated in the same integrated circuit, then most likely, no, these parameters will be identical for both Q1 and Q2. Okay, Q1 is what we call a diode-connected MOS transistor. Q1 is a diode-connected MOS transistor. Okay, if you have a MOS transistor, in this particular case, NMOS transistor that looks like this is equivalent to this. Okay. Now, first of all, this is always saturated. Why is that always saturated? That's always saturated because VGS is going to be equal to VDS. No? If you take a look here in the left, this is VDS, which is equal to VGS. No? Therefore, VDS will always be greater than VGS minus VDH, which is VDS sat. No? That is why always saturated. Okay. Now, for current to flow, for example, you have a diode-connected MOS transistor. For current to flow, then the drain has to be made positive with respect to the source. The drain has to be made positive with respect to the source. No? That's equivalent to forward biasing this diode. If the drain is negative with respect to the source, this will no longer be saturated. This will be actually cut off. No? And current will not flow. Okay. So that's the diode-connected MOS transistor. Okay, but that's not what we want to discuss. No? If you take a look at Q1, what is your expression for IREF? IREF is equal to 1/2 KN1 VGS minus VTH squared. 1/2 KN1 VGS minus VTH squared. Let's neglect channel length modulation. Neglect channel length modulation. Now, if you take a look at Q2, you have I sub D is equal to 1/2 KN2 VGS minus VTH squared. Notice that VGS for Q1 and Q2 will be the same because their gates are both connected to each other and their sources are also connected to each other. So this is the same for Q1 and Q2. Therefore, if I get the ratio of ID to IREF, I get the ratio of that. That is simply equal to Kn2 over Kn1. This, the 1/2 will cancel out, and then these two terms will cancel out. And Kn2 over Kn1, we know that this is use of n COX W2 over L2, and then this is muse of n COX W1 over L1. So this will also cancel out. So I'm just going to get W2 over L2 all over W1 over L1. Now, this is a significant result. Why? What are we saying? Okay. If I establish a value of Iref, and I can do that by having a constant current source here. If I establish a value of Iref, then I can establish any value of ID here by just properly getting the correct ratio of the form factor of Q2 with respect to the form factor of Q1. So kung na-establish ko na tong Iref, I want a certain value of ID to bias this transistor. Remember, no, I want to establish this I sub D because this is what biases this transistor. Then all I have to do is correctly get the form factor ratio that I want. As a matter of fact, if the form factors are equal, if the form factors are equal, okay, then ID will just be equal to Iref. So I summarized that in this slide. Iref and the dimensions of Q2 relative to Q1 can be used to establish the bias current ID. Now, may proviso dyan, no? We have to make sure that this stays in saturation, because if this does not stay in saturation, then this equation will no longer be true. Rather, this equation will no longer be true. So we have to make sure that this transistor stays in saturation. Now, the nice thing about this is you can have a single reference that is used to derive the bias current of several transistors. So here, I'm using this reference to establish the value of I sub D. But I could have had, I can connect this to more transistors. I can connect this to another transistor here, let's say Q3. Okay, where this is ID3. Okay, maybe another transistor here. Let's say Q4. And I want to establish now here ID4. Okay. So the important thing is they all have the same VGS. No? And then if I want a certain value of ID3, I just have to size this properly with respect to Q1. No? If I want a certain value of ID4, I just have to size this transistor properly with respect to Q1. So just the ratio of the form factors. Okay, again, I have an exercise here. I'm going to leave this to you to figure out on your own. No? Okay, remember that we disregarded channel length modulation. What will happen if we don't disregard channel length modulation? Then our equation for our current is going to change. This is to take into consideration channel length modulation. Takes channel length modulation into consideration. Where if you recall from our previous lecture, lambda is your channel length modulation parameter. So you have this for I1, this for I2. When I get the ratio of the two, then I have to take into consideration of these terms. 1 plus lambda 1 VDS1 and 1 plus lambda 2. No, sorry, this should be lambda 2 VDS2. I will make the corrections in the slides later on. Okay, so that is the end of the discussion on biasing. Okay, what did we show in this presentation? That an NMOS transistor could be used as an amplifier. However, it does not deliver as much gain as a BJT. We re-emphasize the importance of selecting a proper cue point. I introduced a fixed bias scheme. Fixed bias in this particular case, meaning we fix the gate voltage. Okay, but we showed that just fixing the gate voltage is not enough. The cue point tends to be unstable. And to make that stable, we have to add a source resistance to the between the source and the ground. And then I also showed you that another way of establishing a bias point, which has some amount of stability, is your drain to gate bias, by simply connecting a resistor between your drain and gate. It is relatively stable. However, there are trade-offs because you can only adjust one particular parameter, and that is your drain resistance. And then I also showed you how you can bias your MOS transistor using current mirrors. This is an important technique that is used particularly when you're designing amplifiers in integrated circuits. Before I leave this topic, are there any questions? Because I'm going to move very quickly to our next topic. Are there any questions? Give me a sign, guys, either yes or no. Okay. At least somebody is listening. Only one person that heard me? Okay. Thank you. Thank you. Thank you to Bian Rosel and to Baron. And okay. Thank you, everyone. No? At least finally, I'm getting some reaction from you guys. Okay. So let's move on to the next topic. Okay. MOS Transistor Amplifier Topologies. Okay, what do I want to cover here? I'm going to discuss the common source, common gate, and common drain amplifiers. Okay, I will be characterizing this based on their large signal models, and we'll also do some comparison of the different topologies and also compare this with the BJT topologies. So this is your three topologies. Your common gate, I have both the NMOS version and the PMOS version. Sorry, common source rather, not common gate. In the common source, your input is at the gate, your output is at the drain. For your common gate, your NMOS version and your PMOS version, your input is at the source, your output is at the drain. And finally, the common drain, NMOS and PMOS, input at the gate, output at the source. So just like the BJT, the common terminal is with respect to your time varying input. It's with respect to the AC component of your input signal. So the input signals I showed here, VI, notice that that's V capital I. That implies that the bias is already incorporated into your input signal. So when I say V capital I, V capital I, V capital I, so this already includes the bias voltage. So what did we say that to be? No, you have V capital I is V capital I plus small v small I. So this is the signal that we want to amplify, and this is your bias voltage. Okay, let's first take a look at the common source amplifier. So your NMOS version and your PMOS version. So these are the equations that by now you should know by heart. These have been introduced to you in EEE 123. You've used it in many, many computations already, and therefore you should know this already by heart. So I can use these equations, and I'm not going to go through it anymore because we've had plenty exercises there. No, but for an NMOS example, just as this, so these being the parameters of the circuit, I can use these equations to generate this table. So I just have a set of input values and a set of output values. Okay, the thing that you have to be able to do is you have to be able to determine when the transitions are. So this is your transition from cutoff to saturation. So I call this point A. And then this is your transition from saturation to linear. I call this point B. By the way, I also labeled a third point here, point C, which I said is deep in linear. So I have here the description of A, B, and C. Okay, notice that in my saturation region, I made my steps, no? I made my steps a little bit smaller because I wanted more data in my saturation region. Okay, so this is now my cutoff. Okay, you see, this is your cutoff. This is your linear region. And then from here to here, this is my saturation. Okay, and we said that, okay, if we bias our transistor, we bias this, we would want to bias it somewhere in the middle of your saturation region. We don't want to bias it too close to A, and we don't want to bias it too close to B. We want to bias it somewhere in the middle because that's where your voltage transfer characteristic is almost a straight line. If your voltage transfer characteristic is curvy at the point of bias, then there's going to be some distortion. So I show that again here. You'd like to bias it somewhere here in the middle, no? Not somewhere close to A and not somewhere close to B. By the way, no, what is the value of VDS at B? At B, the value of VDS is VDS sat, which is just the value of VGS at point B minus VTH. No? So this is VDS sat. And that's how you determine where the transition is. I think we had an exercise like that in class, no? Where I told you, okay, compute where the transition is. You have to set VDS to VGS minus VTH. Okay, just another perspective. Again, I already showed this in class. This is your load line equation. What is your load line equation? Your load line equation, this is KVL applied to supply to ground through the drain and source. No? So applied to the drain to source circuit. No? Circuit. So this is the equation of my load line. Or rather, no, this is the plot of my load line on my drain characteristic curves. I would select a Q point here. I don't want it to be too near B because I go into my linear region. So if I go up here, this is already the linear region. I don't want it to be near A because I will go into cutoff. And as my input signal is applied, as V small I is applied, my operating point actually goes along this line this way. Okay, the gain. How do we determine the gain of our amplifier? Just a while. Okay, how do we determine the gain of our amplifier? The gain is actually the slope of the VTC. Because the slope of the VTC the slope is change in voltage over change in output over change in input. No? So if you get the slope of the VTC, that is actually the gain of your amplifier. Okay. So how do you compute for the gain? No? Okay, what is your output? No? So going back to this circuit, so this is RD, this is VDD, this is VI, and this is VO. No? And then notice that VI is VGS, and VO is equal to VDS. So you have ID is equal to 1/2 Kn VI minus VTH squared. No? VO is equal to VDD minus RD times ID. So this is going to be VDD minus RD 1/2 Kn VI minus VTH squared. And my gain is dVO over dVi. That is equal to my gain. And if I just get the derivative of this function with respect to Vi, what am I going to get? The derivative of VDD is 0. So I'm going to get minus RD, okay, 1/2 Kn. So this is a constant. Then the derivative of this polynomial. But the derivative of this polynomial is going to be 2 Vi minus VTH. So this cancels. So finally, my gain is just going to be minus RD Kn Vi minus VTH. This is in saturation. No? In saturation. Okay. So I can use this equation to create a table, input, and gain. Of course, it's going to be different in linear mode. No? In linear mode, okay, what do I get? I get VO is equal to VDD minus RDID. But what is now ID? ID is going to be equal to K VI, which is VGS, minus VTH, minus 0.5 VDS, but VDS is V sub O, multiplied by V sub O. Okay. If I wanted V sub O in terms of V sub I would have to get a simple expression V sub O, and then all the terms on the right will just be V sub I. No, it's difficult, no? I cannot get an expression for V sub O in terms of V sub I. No? Maybe for individual values of V sub I can, no? Because that's going to be quadratic, no? But not a general expression. But I can get an expression for V sub I in terms of V sub O. So let me go to the actual slide. No? Here. No? So this is my V sub O in terms of V sub I. I cannot isolate V sub O to put it on the left side like this. No? But I can isolate V sub I and put it on the left side like this. So here I have an expression for V sub I in terms of V sub O. So the trick I can do is I get the derivative of V sub I with respect to V sub O, and then I get the reciprocal of that, and that will be my gain. And if I get the derivative of V sub I with respect to V sub O, I'm going to get this very nice equation here. So try this as an exercise. This is just an exercise in getting derivatives in differentiating. So just differentiate this equation. V sub I with respect to V sub O, and then you should get this. And I can use this equation now to plot my gain. And so that's what I did. No, I used this equation for saturation, this equation for linear to plot my gain, and this is what my gain will look like. Okay. So things to note, no? First of all, your gain is negative. Okay. And then your gain, as you increase your input voltage, your gain increases. In fact, your maximum gain is achieved in the transition from saturation to linear, no? So the gain increases as the bias, as the Q point increases, no? Now in the linear region, I still have a certain amount of gain, but very small. Okay. And then as I go deep into the linear region, my gain approaches zero. So this is how my gain profile will look like. So just like the BJT, I may opt to put my Q point slightly right of center because I want to take advantage of higher gain. Now, the thing that you notice here are, okay, the gains are negative. The values are small. These are small compared to the BJT. Because if you recall the BJT, the gains can go up to the hundreds. Okay. Other than that, the common source is similar in characteristics to your common emitter. So this is for your MOS, this is for your BJT. Okay. Now, I just wanted to throw this in, just show you that we could have done the same thing with the PMOS. So this is your NMOS. We could have done the same with the PMOS. The formulas we would have used for the PMOS would have been this. Okay. And for the PMOS, where are we now? Sorry. Yeah. No, here. Okay. For the PMOS, okay, our expressions for, well, anyway, the voltage transfer characteristics. If you take a look at the voltage transfer characteristics, as we increase our input from zero, in the NMOS, we start in cutoff, then we go to saturation, then we go to linear. But when your input is equal to zero, right away we're deep in linear. So this is point C. You are deep in linear. Why? No, because when your input is zero, if Vi is equal to zero, that's when your VSG is maximum. That's when you have a very large source to gate voltage, when your input is zero. And that's what puts it deep in linear mode. No? And then this is your transition, this is your point B, and then your point A. No? So in the PMOS, it's different. As you increase your voltage, you go from linear to saturated to cut off. Otherwise, the curve looks the same. You still have a curve that produces a decreasing output voltage as you increase your input. Notice that your saturation region is now farther to the right. So this is how it would also have looked for your PNP common emitter. So your PMOS common source okay, the BJT partner of this would be your PNP common emitter. And we can get the gain in the same manner. So this is going to be my expression for my output voltage with respect to my input voltage. Notice that my output voltage is simply equal to I sub d times R sub d. I sub d times R sub d, where I sub d is 1/2 K sub P. Okay, this is VSG. Note that VSG here, VSG is VDD minus VI. So this is VSG. And then we deal with the absolute value of VTH. And therefore, if I get the gain, which is just the derivative of V sub O with respect to V sub I, it is just this expression. Just that expression. So I can use this to create my table. And in the linear region, again, you can play a trick, no? You can get the derivative of VI with respect to V sub O, and then just get the reciprocal. So again, you can try this as an exercise. I didn't put the result here anymore because it's quite long, but what do we want to do? We want to use the above to create a plot of the gain of the amplifier, and this is what we get. So still positive gain, okay? But this time, as you increase your bias, your gain is decreasing. So if we want a high gain, we want our bias to be somewhere left of center. Okay, let's look at the other topologies. For example, this is your common gate amplifier. Okay. Common gate amplifier, simple thing to do would be to ground the gate. But that's not the only way we can implement a common gate amplifier. Later on, I can show you that the gate does not necessarily have to be grounded. But if the gate is grounded, this is now going to be VGS. Okay, and V sub I is now going to be negative of VGS. Because take a look at the polarity, plus minus. So V sub I is going to be the negative of VGS. And for this to operate properly, because we have to establish a positive value of VGS, then you're going to have to bias your input with a negative voltage. That's what you're going to have to do. Anyway, this is your formula for I sub D in saturation, where this is I sub D. Okay. Where this is VSG, no, sorry. Yeah, sorry, VGS. This is VGS, not VSG. And therefore, this is V sub O. So I can use this again for my table, to create my table. And then in the linear region, my formula for I sub D will be, okay, a little bit, here is this. Formula for I sub D will be a little bit more complicated. Again, you recall that this is VGS. Okay. And then you have to remember that this VDS is equal to V sub O minus V sub I. That's this VDS. VDS is V sub O minus V sub I. So this is the expression you come up with. Unfortunately, for a given value of V sub I, you're going to have to solve a quadratic equation. No, it's not going to be a simple formula that you can use. It's a quadratic equation. Okay, I have here an exercise. This is supposed to be for you to determine the output value for 3 different input values. And then I also want you to, this is just as an exercise, I want you to determine where the transition is from saturation to linear. The answers are already in this table. But please try this on your own. This is just for you to practice. So this is the VTC. This is the VTC. Okay, at VI, remember what we said earlier? For VGS to be positive, V sub I should be negative. No? In other words, we have to bias our input with a negative voltage. So notice here that the values of my input are actually increasing in magnitude but are negative. Saturation is here because 1 volt is the transition from cutoff to saturation. And the transition from saturation to linear is at negative 3.97 volts. So that's somewhere here. No? This is your transition from, here. This is your transition from saturation to linear. No? In other words, this is point A. No? This is point B. And this is point C. No? So this is A, this is B, and this is C. Again, where will you bias it? You will bias it here. Okay. This is your saturation. We don't normally use the transistor here. So this is linear. No? So this is not normally used. No? This region is not normally used. Usually we confine our bias and input signal to this particular region. Of course, we also don't use it in cutoff. Okay, gain. Sorry, there are typos here. Now I'm going to correct the slide. No? This should be R sub D, this should be V sub I, this should be VTH. But this is my expression for my output. My output is VO is VDD minus IDRD. So this is my expression for my gain. This is just getting the derivative of V sub O with respect to V sub I. So I can use this to produce a table of gain versus input. Now in the linear region, this is going to be my equation. My expression for I sub D is going to be more complicated. We already derived that here. This is my expression for V sub O. So this is going to be my expression. And you're going to see that it's not possible to get this derivative or this derivative. It's not going to be possible from this expression. Okay, you might be able to do it, but it will be very, very difficult manipulation if you can do it at all. So what I chose to do is I just approximated the gain of the amplifier in the linear region by determining the slope in the VTC. No, because at any given point here, I can determine the slope by getting the delta of V sub O over deltas of V sub I, through the adjacent points. So that's what I did to come up with this graph. And this just gives you an idea of the gain of your amplifier. So notice that in the linear region, so here, seeing that this is almost a straight line, we can expect the gain here to be constant in the linear region. So that's this. The gain is practically constant. In fact, what is the value? It's about 1. The gain is constant at 1 here. Okay, but we normally use the amplifier here in the saturation region. So this is where it's saturated. And this is where we use the amplifier. Again, you get a greater gain, okay, with a greater magnitude of your input signal, but your input signal is negative. Okay. The common gate, the NMOS common gate, the partner of this with the BJT would be the NPN common base. The NPN common base. No? Take note that the gain is positive. Okay, the magnitude of the gain is comparable to the magnitude of the gain of the common source. Okay, what is our last configuration? The last configuration is the common drain. So you're going to see that the common drain, this time, the partner of the common drain for the BJT would be the common collector. So you can get an expression for V sub O. So this is your expression for V sub O in terms of V sub I. Unfortunately, for a given value of V sub I, you would have to solve a quadratic equation. You can, this is in saturation. In linear, you can also get an expression for V sub O. Again, for a given value of V sub I, you would have to solve a quadratic equation. So that's how I came up with this particular table. So this is my voltage transfer characteristics. Where is my linear region? My linear region is approximately, is here. No? Not linear. My saturation region or active region. That's from here to about 11 here. This is my saturation. This is my linear. Okay. Again, no? You should know how to determine the transitions. So this is your transition. This is point B. This is point B. You should know how to determine the transitions. In both these cases, okay, I have my expressions in saturation for V sub O in terms of V sub I. But in both these cases, it's not going to be possible to evaluate these derivatives, no? It won't be possible to evaluate this derivative. So again, how did I get the gain? I just got the gain by approximating the slope from this curve. And this is what I got. So this is your saturation. This is your saturation. This is your linear. Okay. Note that your gain is very small. Okay. In the saturation region, your gain is less than 1, but close to 1. Okay. In the BJT, the partner of this, no, the corresponding configuration would be your common collector. So the NMOS common drain for the BJT, this would be your NPN common collector. So what do we use this for? We use this as a buffer. That's the purpose of your common drain. Okay. Applying the input and retrieving the output. This is very similar to your BJT. Our starting point usually is a biased transistor. So let's say we have a particular NMOS. The first thing that we have to do, we decide what our operating point is going to be. After deciding what our operating point is going to be, select the proper values of your resistances. So this is what you start with. And then depending on whether it's a common source, common gate, or common drain, you apply your input or your output. If it is a common source, you apply your input to the gate, of course, capacitively coupled. So this is now V small I instead of V capital I, because V capital I would be here in the point where your input and your bias voltage combine. And your output you get at your drain. Again, if you capacitively couple your output, this is V small o, because your V capital O would be here. That's your common source. Your common gate, so again, your gate does not have to be grounded. In our example earlier, when we got the VTC and the gain, we grounded the gate. But as long as you provide a bias to your gate, which makes it positive with respect to your source, then it's okay. No? So notice that that is what this voltage divider circuit does. No? It makes the voltage of this positive, at least the Q point, positive with respect to this. If we grounded the base, then you would have to provide a negative bias here, which is why we made our inputs negative. Okay, so your input is connected now to your source and your output is at your drain, and that's your common gate. And finally, your last configuration is your common drain, where your input is again at the gate and your output is at the source. So these are your three different combinations, all starting with this bias circuit. Just to summarize the BJT versus the MOS amplifier circuit, okay, the partners here are common emitter and common source. Both have negative gain, although the common emitter has a larger gain than the common source. But if you take a look at the VTC and the gain curves, they resemble each other. And then you have your common base, which is comparable to your common gate. Both have positive gain. And in both cases, the magnitude of the gain is comparable to the common emitter and common source, respectively. So if you want to have a positive gain, you use either a common base for a BJT or a common gate for your MOS. And then your common collector and common drain, these are used as buffers. Your gain is approximately equal to 1. Actually, it's lower for a common drain. It approximates 1 for a common collector, or you call it sometimes an emitter follower. So in summary, we can use the large signal model of the MOS transistor to determine the VTC and the gain of any MOS transistor amplifier topology. And if we have a low frequency time varying input, we can use this point-to-point technique to get the response of your circuit to a time-changing input. Unfortunately, it's going to be very cumbersome because we're going to have to do it point by point. For example, if you have a sinusoidal signal, you're going to have to plot this point by point. Fortunately, there's going to be a simpler method of doing this in the future. And this is using the small signal analysis. So we're going to develop in the future, right after this module, we're going to develop the small signal model of the MOS transistor. And then you're going to see that you can use now linear circuit analysis techniques to analyze the MOS transistor amplifier. Okay, that's the end of our coverage of the MOS transistor as an amplifier. Okay, if there are any last questions, I will entertain them right now. Any last questions you might have? Okay. So again, my appeal, please try to master your your analysis, DC analysis of your MOS circuits. No? Um, I just am afraid. No? I'm really afraid that right now you still have not how do you say it? Have not gained confidence in doing these things. Okay. Okay, so that's all. Have a happy undas wherever you are. Take advantage of the break. Take a rest. Okay. Don't forget that there's a deadline for your problem set. I'm going to be posting the quiz uh, for the next module very soon. Okay. Thank you.